The previous video discussed types with variable length, such as arrays, lists, and strings. This video discusses types with a fixed number of values or a fixed range of possible values. The first example is an enumeration, which explicitly takes one value from a range of specific possibilities. Common examples include days of the week or months in the year. Here we have an enumeration in Java that shows the days of the week. This variable has been assigned to a particular value. And we can define conditional statements using switch case that behave differently for different values of the enumeration. So this switch case statement responds to Monday and Tuesday and then treats all other days the same. So if I run it, it'll print out Monday, but I could change it to Friday, run that, get some other day. And currently I don't allow Saturday or Sunday, and so that may be on purpose. Maybe I only want to allow weekdays, or I could add those as options to this enumeration. Strictly speaking, there is nothing that is accomplished with enumerations that can't be easily accomplished with named integer constants, but enumerations are more readable and provide the added benefit of some type checking. If the enumerated values correspond to integers from 0 to some max value, then those numbers can be easily accessed as follows. So if I run this code with the day set to Tuesday, it prints out a 1 because Tuesday is the second day in this list and the numbering starts at 0. If I change this value back to Monday and run this, I'll get a 0. Like so. In C, enumerations simply are integers, which means they aid readability, but they don't really increase reliability because C has so many unchecked type conversions. As we can see here, I can create a month and assign to it the value Feb for February, and if I print this out and show the value as an integer, it'll show us the value of 1 because we're counting 0 then 1. But I can also directly assign a value of 4 to a month variable and even a value of 20, and this is the real problem here. And so let's see what happens when we run this code. When I assign the value of February, it associated with that variable the integer value 1. When I assigned an integer value of 4, I was able to do an equality check to make sure that the variable m2 was May. So that does provide some flexibility. But then we see the case where we have a problem with error checking and type checking because I can assign a value of 20 to m3, which is not a month at all. Haskell's data keyword also allows enumerations to be defined, as well as several other more complex data types. Pattern matching on the enumerated values is allowed, as shown in this function I've defined called performOp, where I simply have a distinct case for each of the potential enumerated values. This sort of data type is most useful when the different values correspond to very different behaviors, as with this arithmetic example. Each operator corresponds to a completely different function definition. Rather than make a distinction between several distinct possible values, we might want to make a distinction between having a valid value and not having a valid value. Such types are known as optional types and are built into Haskell as part of its maybe type. This constructor information says that a maybe type can either be nothing or just with a value. An example is the following. Here we have a guarded division operation, x divided by y, but if y happens to be 0, then we will return nothing. Otherwise, we will return just the result x divided by y. So this is an example of producing a maybe type. Then here we have an example of using a maybe type as input using pattern matching. If the result is a just x, we'll indicate that the result is the value of x. If the result is nothing, then we say the result is invalid. Here are some examples of how we would use this. Result, guarded divide 4, 5. The result is 0.8. But if I change the 5 to a 0, the result is invalid. Such optional types are also supported in C#. A normal int type must contain some integer value, but if initialized with a question mark, as these types are, it makes the primitive type optional, meaning that it is allowable for that variable to store a null. If I run this code, I get the following result here, 27 and invalid. That's because this test function takes an optional type. If it's null, we print invalid. Otherwise, we print the value. Naturally, normal object types are also considered optional because they can also have null values. Object references in Java are also optional types, and although Java's primitives cannot be made optional, one can use Java's wrapper classes to have optional versions of any given primitive type. Just as with the C# function, if we explicitly define this parameter as being the class integer rather than the primitive integer, that allows us to check if its value is null and get this sort of output here. A Java class is a collection of named fields and methods. Although this example has some fields and a constructor, but doesn't have any non-static methods. This static main method is just a way for me to test out this class. Essentially, all I'm doing with this employee class is providing a way of associating several pieces of data with a single variable, such as this variable e defined here. And when I run this, I can access the individual components of e by their names. Because I don't have any methods manipulating this data, this class is actually an example of a simpler type known as a record. Records existed before object-oriented programming and also exist in some languages that have been developed since the advent of object-oriented programming. In C, records can be implemented using a struct. So a struct is simply a name type with some named fields, and I can initialize a new struct variable with a comma-separated list in curly braces. The order of the items here corresponds to the order in which these field names are declared. And I can access the individual fields using the dot operator. And I can also change the individual fields using a dot operator. So let's run this code. So we see the point printed out in terms of its x and y values, and then I change the x value, and now I'm printing that out. Although structs do not have any methods, complex data types can be built with structs. Here is an example of a linked list of integers. The struct node is an int data, and then a pointer to another node. I'm initializing an array here, and recording what its length is. The node head will be the head of a linked list, and this first loop loops through the length of the array and assigns each array element to the data portion of a new node struct. I'm creating these nodes using the memory allocation function of C, which grabs free memory space from the heap. After this loop, I iterate through the linked list structure, starting at the head, going until I reach a null pointer, and moving the current to the next node at each iteration, and simply printing out the values. So if I run this code, I get 1, 2, 3, 4, 5, which were the values inside of that array, which were successfully transferred to the linked list. Of course, working with this representation requires the programmer to understand a lot about what is happening with the underlying implementation of the struct, and is far more complex and error-prone than working with abstract data types, which hide the implementation from the user. This is part of the motivation for classes in C++, Java, and other languages. Common Lisp also supports structures via its macro defstruct. The first parameter is the name of the structure, and the following ones are the names of fields. I can create a new instance of this structure using the function makeVehicle. So this function was automatically defined when the structure was created and takes parameters for the make, model, and year. Now if I want to save this instance of a vehicle in a variable, I can use this setQ function. So now I have a variable Versa that contains that vehicle instance. And the defstruct macro also defines some functions for accessing the individual members of the vehicle. For example, vehicle make returns Nissan because vehicle is the name of the structure that I defined, and make is the name of the field that I'm accessing. Similarly, I can have vehicle model and vehicle year. Haskell can also represent records, once again, using its data keyword. In this example, I have actually named the individual fields and given them types: make, model, and year. I can interact with this record by using positional arguments, or I can access and modify individual fields. Now note that because Haskell is a pure functional language, I don't actually modify the fields. Rather, what I do is I create a new instance in which all fields are the same except for the ones that I change. So I can take this initial car and I can create a new one that is the same as X, except I will change the model and the year. Note that in the result, the make is still Nissan because that's what it was in the original value of X. However, if all you need is a simple way to store or return a collection of data without worrying about assigning names to each field or giving a name to the type, then a tuple is sufficient. Here is a tuple which contains the same information as the car data structure which I just defined. The values in a tuple are positional. So if I want to get the model from my tuple representation, I would have to use pattern matching like so. So I can reload this. And if I call getModel on that tuple, it returns Versa. Python also has tuples. The values in a Python tuple can be extracted via pattern matching. but they can also be accessed via subscripts. Tuples in any language are convenient because they provide an easy way to return multiple values from a function. In Haskell, you can never change any data because it is a pure functional language. In Python, you generally can change variable values. However, when it comes to tuples, you are not allowed to change them. They are immutable. So what do you do if you want to change a tuple value? You just convert it to a list, and then here you can change the list, and then once the list is changed, you can convert it back to a new tuple. Now let's say that instead of having a function that returns multiple values of different types, you want to have a function that returns exactly one value, but it could have either one type or another. Well, because Python uses dynamic typing, it really doesn't care what the return type of your functions are. So I can define a function, test, that sometimes returns an integer, but sometimes returns a string. And Python doesn't mind. There's 25. There's the string hello. But how would you handle this in a statically typed language? C and C++ handle the problem of multiple possible return types with a data type called a union. Now, unfortunately, as with many operations in C and C++, unions are not type safe. They don't do any type checking. So, although they have some useful applications, they can also allow for some weird programmer mistakes. So this union, named data, is either an int or a double or a character. But these three fields are named. Now, once I've declared a data variable, I can assign any one of those fields a value. However, if I then try to access one of the other fields, it's actually accessing the exact same value. When I change one, I'm really changing all the others, because I do not have multiple distinct fields as with a record. I really only have one slot of memory and 3 different names for accessing it, according to different sorts of types. So when I run this code, you'll see that when I interpret the value as an int, but print out the fields for the int, the double, and the character, I get the value 20 for both the int and the character. The reason I get this weird value here for the double is that the double uses more bits in memory than the int. So the value I'm getting here is the combination of the bits for the int along with some random garbage bits in memory that happen to be in that cell before I initialize that variable. When I then move on to print out the double, the reason I'm getting a 0 here is because, remember, I've reassigned at this point x.d to be this floating point value. That also overwrote the 20. But I don't get 133.54 and I don't get 20. The reason for that is that when I do x.I, I'm only looking a portion of the bits that are used to represent that double, although it does work for the character unusually. And then I also reassign the union value here. I set x.c to the character a, and when I print out I as a character, I get an a. When I print out d as a character, I get nothing, because I have those extra bits that are interfering with the display. And then when I print out the actual character field, I get the a. So although this does allow me to store multiple possible types, or more accurately, one of several possible types in one memory location, the fact that there's no checking makes this a bit dangerous to use. This is known as a free union or undiscriminated union. In contrast, Haskell's unions, once again defined with the data keyword, are discriminated unions. So explicit acknowledgement of the type being worked with is required by the programmer. What I have here is a type named data, and it can hold either an int, a double, or a char, but I have to specify a specific identifier with each of these. Now, these labels could be anything, I just happen to choose one-letter abbreviations. If I use this in a function, I will once again use pattern matching based on those identifiers that then precede the values so that I can interpret different types of values in different ways. Let's see what it looks like when I run this function. Explain union I6, the int 6, the char y, the double 8.546. Because it is not possible for me to store a double value using the I identifier, I will never make the kind of mistakes in Haskell that are allowable in C. Languages like Java and C# do not support unions, but there are more elegant workarounds that can be achieved using inheritance and other object-oriented principles, which we will discuss later.